Hello gals and guys, Mr. Ambrose here with a video on inverse trig function derivatives. And now before I go into the derivation for the derivative of the inverse of the sine function, I just want to go over one or two things with you guys. And first is that while this is how we perhaps notate the inverses of the respective sine function, cosine function, and tangent function, another way that we express these inverse of these respective trig functions is by calling the inverse of the sine function as arc sine of x, the inverse of the cosine function as being arc cosine of x, and the inverse of this tangent function, we denote that, or can denote that also with arc tan of x. So just something to be mindful of, that if you see these expressions, they just represent the inverses of those respective trig functions. The other thing I want to make note of is the fact that we have this -1 after each of our respective trig functions, and again, that means the inverse of those respective trig functions. So please don't consider this to be equal to this here. This here means we are raising the sine function to the -1st power, which a way to perhaps rewrite that would be to take sine function and bring it down into the denominator of fraction. And while these two expressions here are definitely equal to each other, they're not equal to the inverse of the sine function, right? Because 1 over the sine of x, we technically know is equivalent to the cosecant function, and that's its own separate function. And so be mindful of the fact that if you see a -1 after any one of your trig functions here, this represents the inverse of that respective trig function. So now what I want to try and determine next is, well, what is indeed a derivative of our arc sine function, or inverse sine function? And to help do that, as we've done with other functions and trying to derive their derivatives, we're going to use everything that we have at our disposal to help us accomplish this. And a way that we sometimes try to evaluate the inverse sine of x is to try to think to ourselves, well, the sine of what angle gives me this x? That's a way to sort of think of this inverse sine function. And so because of that, I'm going to rewrite this inverse sine function in that manner. Again, when we think of inverse sine, we're thinking about the sine of what angle, here y, gives us this expression of x. And so technically, right, these are equivalent. And since they are equivalent, we can work with this here. And in this equation, right, we have the sine function, whose derivative we know what the value is, and we definitely know what the derivative of x is. And so we can derive this equation implicitly with respect to the variable x. And so that's exactly what I'll do. And so the derivative of sine of y with respect to x, perform an implicit differentiation. We know the derivative of sine is cosine, and it'll be cosine of y. But because there's a function inside that y there, we need to multiply this by dy dx. And then the derivative of the right-hand side, the derivative of x, we know is just 1. And then solving for dy dx, we get that dy dx is equal to 1 over the cosine of y. And for your test later this week, it's okay to leave your derivative this way if you're just looking for the derivative dy dx. But again, I want a derivative rule that is solely in terms of the variable x, because that's what all our derivative rules have been in terms of the variable x. And that's because our original functions have all been in terms of x. So I don't want to leave my answer like this here. Now, as we perhaps did with other situations, we could perhaps substitute the inverse sine of x in for y here, but I don't want to even deal with something as convoluted as cosine of the inverse sine of x as part of my derivative answer. There's perhaps a simpler version for a derivative here, and to come about what that will be, I'm going to revisit the I guess, original derivation of our trig functions, and that's through right triangles. And so if we, again, we're starting off technically with this expression here, which is equal to this here. And now if you recall, when dealing with right triangles, in a right triangle, we have angles in here. We have acute angles. And in the way that this has been all set up, the angle here would be denoted by y. And so I'll put perhaps y right over there in our right triangle. And when evaluating perhaps the sine of an angle in a right triangle, we can always think of that by using SOHCAHTOA. And since sine of y is equal to x, in order to apply SOHCAHTOA, we can think of x as being x over 1. And so using SOHCAHTOA, the sine of y should equal the opposite side, which will be x, over the hypotenuse, which is 1. And again, I'm getting that just based upon this expression here. And now I have this right triangle, and I really want to, get something in for the cosine of y here. And we can do that. We can evaluate the cosine of y if we knew what this adjacent side is, right? Because in SOHCAHTOA, the cosine of an angle is equal to the adjacent side over the hypotenuse. So we can solve for this adjacent side because we know what the other two sides are of this right triangle, and we can solve for this missing side by using the Pythagorean theorem. And so I will perhaps label this side as b. And so we can write, using the Pythagorean theorem, x squared plus b squared is equal to the hypotenuse squared. And solving for b, we can subtract both sides by x squared. And 1 squared is equal to 1. And then we can take the square root of both sides and get that b is equal to technically plus or minus the square root of 1 minus x squared. But because we're dealing with a physical object here, normally we just use the positive value when dealing with measurements of geometric figures. And so because this leg here is equivalent to the square root of 1 minus x squared, then I claim that we can evaluate the cosine of y. The cosine of y would simply be the adjacent side of 1 minus x squared all over the hypotenuse, which would just simplify down to just 1 minus x squared. And then that's what a cosine of y is equal to. So for our derivative here, we can substitute that expression in of 1 minus x squared all underneath the square root in for the cosine of y. And so this is our derivative rule that we have for the arc sine of x. The arc sine of x is equal to 1 over the square root of 1 minus x squared. And for your exercises for today, this is what you're going to want to use to apply when you have to derive the inverse sine of x. This is the rule that you want to apply. And note that like this x here is just equivalent to that x that was in, or whatever the argument was in for the inverse sine of x. And so again, this is our derivative rule for the inverse sine of x. And you can go about the same sort of process that I did here to ultimately get this derivative rule for our derivative rules for inverse cosine of x and inverse tangent of x. But I will just give you what those rules are. And so the derivative rule for inverse cosine x is just -1 over 1 minus x squared. So if you notice, this is very similar to inverse sine of x. It basically is the same thing, except this is negative. And the derivative rule for inverse tangent of x is equivalent to 1 over 1 plus x squared. Okay, and so these are your last of all your trig functions, or your functions in general, and derivative rules that you have to have memorized for your test this upcoming week. And so for the rest of today and for the class period, I ask that you guys now try to work on those problems that are on that sheet. And my solutions are also posted so you can check your work. And tomorrow when we reconvene class, I'll go over any questions you may have on these exercises as well as the homework from last night. So I hope that this video helped illustrate what our derivative rules are for inverse sine, inverse cosine, and inverse tangent. And I hope that you guys enjoy the rest of your day. Take care, everyone.